So back in the 1700s and the late 1600s, mathematicians were studying four major problems. First one was the tangent line problem. How do we find the slope of a tangent line? And then that kind of correlated with the velocity and acceleration problem. How do we find instantaneous velocity and instantaneously acceleration? And then that also ties into something called the minimum and the maximum problem. How do we find minimums and maximums in a function? And finally, the area problem. How do we find the area under a curve? So these are four big questions that all kind of relate together. And these first three really tie together with something called derivatives that we're going to be studying. So lots of mathematicians were studying these, but there's two that kind of stand out. We got Gottfried Leibniz and Isaac Newton. And these two guys were kind of in competition together, and it's kind of an interesting story if you want to look into that there. But these two guys were competing to have their name as the person that invented calculus, and there's a big debate that goes on still who is responsible for the invention of calculus. And it's really kind of interesting how they both came up with their own version of it, and the two different versions are useful. So as we study calculus, we'll use ideas from Isaac Newton and ideas from Leibniz. So let's start by investigating this tangent line problem. So here's the big idea, all right? We have a function like f of x equals x squared, and we want to know if we pick a point, what is the slope of the tangent line at that point, all right? So remember, a tangent line is a line that crosses at one point. Okay, so here we have this parabola, this red parabola, and we want to know what is the slope of the line that just crosses through here. Let's see if I can draw it. We get a line here. So if we have a line that just crosses through and just touches the parabola at that one point, maybe kind of like this green line here. So what is the slope of that line? That's the question. Well, if we take this blue line here, this is what we call a secant line. And so a secant line will touch at 2 points. And we can find the slope of that. That's just rise and run, right? Rise over run. So let's say we have 2 points going through 1, 1, which is the point we want to focus on, and we're going to get closer to. And so what's the slope here? Well, we have f of 1 minus, so the f of 1 is this y value here. So this is f of 1 here. And this is f of 0.5. Well, f of 0.5 is 0.5 squared. And so this is 1 squared minus 0.5 squared all over 1 minus 0.5. Okay, and that's going to come out to be 1 minus 0.25 all over 1 minus 0.5. This comes out to be 1.5 if you use a calculator. All right. And if we use our calculator here, we got 1 squared minus, let's get a little closer now. Let's go to 0.9. So 0.9 is going to be a little closer. 0.9 is over here. I'm going to find let's make another line that now the 2 points are closer. And we want to find the slope here. So we have 1 squared minus 0.9 squared all over 1 minus 0.9. So the x's, the y values divided by the x values, because the y values are just x squared in our function here. And that comes out to be 1.9. And then if we get even closer, let's pick 2 points that are even closer, really close, so close we can barely see here. And if we take those 2 points and we find the slope between those 2 points, so that we're getting real close, we're almost basically the same points. So we got 1.9, so this will be 1 squared minus 1.99 squared all over 1 minus 0.99. Okay? Oh, I'm sorry. This should be not 1.99 squared, just 0.99 squared. All right, and that's going to come out to be 1.99. So you can plug that in your calculator, and it comes out to be 1.99. Well, what are these numbers getting close to? They're getting close to 2. All right, and the closer we get, it's going to get to be like 1.999999. It's going to be really close to 2. So based on these observations, the rate of change, how quickly it's changing here, the change in y or the change in x, that's the rate of change. At x equals 1, well, it looks like it's going to a slope of 2. Okay? All right, well, that's the question. Well, let's generalize this by picking 2 points that are h units apart, and let's find an expression that we can find the limit of to see what it's going to. All right, we're going to use our limit ideas here. So, coming back to our drawing here. Okay, so let's think of it like this. All right, so we're going to take 2 points. We're going to take one that is over here at 1 plus h. H is just some general number here. Okay, so that's right up here. Okay, roughly. Okay, and so this has a value of an x value of 1 plus h and a y value of f of 1 plus h. And the question is, what's the slope here? What's the rise and the run? Okay, so we've got 1 plus h, comma f of 1 plus h, and we've got 1 and f of 1 here. Okay, so let's write the slope function out there. Okay, so we're going to generalize this. I'm going to call this d of 1. All right, not d of x yet. We'll go d of 1 right now. So, all right, well, this is going to be d of 1, which is going to be just the slope. Okay, so the slope of that function there is f of 1 plus h minus f of 1 all over 1 plus h minus 1. Okay, that's just y minus y over x minus x. So using our function, fx equals x squared, we can say this is equal to 1 plus h squared minus 1 squared all over, and we can go ahead and simplify this. This 1 minus this 1 can go away. Now these parentheses were important to start, but now we can just erase them because there's nothing in front. So that's h. And hopefully we can square this easily, right? We square the first, square the second, and then multiply and double for the middle term. 1 squared is 1, h squared is h squared, and in the middle we have 1 times h doubled, and minus 1. Okay, so that became this. Great. And now this 1 minus this 1 is going to go away. And now we're down to this. So d of 1 is 2h plus h over h. Okay. Squared. Forgot my squared there. And great. Well, we can factor out an h here. And those cancel. Basically, we're just canceling an h in both terms. You can think of it that way also. And we're left with 2 plus h. All right. So what does this mean? Well, what this means is we can now want the limit as h goes to 0. So if we say, let's go back to actually this previous one. So the limit of d of, we're going to say 1, because this is specifically at 1. This is the limit as h goes to 0 of 2h plus h squared over h. If we plug in 0 here, this goes to 0 over 0. But that doesn't tell us anything, right? So we have to go clean this up like we just did a second ago. This is just 2 plus h. H cancels both ways like we did down here. And now as h goes to 0, we can plug in 0. This is just 2 plus 0, which is 2. All right. So that means the slope of the tangent line, because the tangent line is when these 2 points become 1, when the distance between this point and this point is nothing. When h goes to 0, these 2 points are 1 point. The slope of the tangent line at x equals 1 is 2. Okay, so we kind of proved it there. Okay, before we just, here we just approximated it and made a conjecture. Okay, so now we've kind of proven it. Let's do this a little more general now. So we want to generalize this here. Okay, so what we're going to do is we're going to take 2 points. We're going to have some random point here, x, f of x, all right? And then we're going to have f of x plus h there, all right? The question is, we want to know what is the slope here at this point x, f of x. But we'll start by looking at this secant line, okay? And we'll see what happens when these 2 points get closer together. What will the slope of this tangent line actually be? Okay, that's what we're going for. All right, well, let's do the same idea. Okay, so we're going to call this d of x now because x can be anything. And that's just the slope. This is the slope at that point x. So we have f of x plus h minus f of x. That's the difference in the y's over the difference in the x's. And that's x plus h minus x. Okay. Well, we're still using the function y equals x squared. So this is specific to that function. Okay. And we're going to want, let's keep in mind, we're going to want the limit as h goes to 0. So we want the slope at the tangent line. So we're going to need that limit. All right, so the limit as h goes to 0. On top we have x plus h squared. That's the y value at x plus h. And we're going to have x squared minus x squared. So that's f of x plus h minus f of x. F of x plus h minus f of x. And then the bottom here, well, these x's cancel, and that just leaves us with h. So a little cleanup here. Limit as h goes to 0, we have x squared plus 2xh plus h squared. So that's the first thing squared, the last thing squared. Multiply and double. Don't forget that middle term. All over h. Okay? Well, this cleans up a little bit. The x squared minus x squared, that goes away. And we're landing on the limit as h goes to 0 of 2xh plus h squared all over h. Can we plug in 0? Will it help us for h? Well, if we plug in 0 here, we're going to get 0 plus 0 all over 0. And that's 0 over 0. That doesn't help us, so we need to use one of our strategies. And our strategy is to simplify like we just did. So we can factor out an h, or you can think of it as dividing both ways. Divide both of these by h. Okay, it's just going to cancel that squared. So we have 2x plus 1h. And now we can find that limit, right? Now you can plug in 0, and we can say that this is equal to 2x. And we're done. Okay, so we have an x in our answer. So here's what we're saying. We're saying d of x equals 2x. What does that mean? This is the slope of the tangent line. In other words, if we take this, look at this point, I don't know, on this graph, this is what? This is about 0.7. Okay, so if we had an x value of 0.7 like this, then what this is saying that at 0.7, the slope should be 2 times 0.7, which is 1.4. Okay, so well, let's think about that. So the slope of this little black line that I drew there, is that about 1.4? Well, a few minutes ago, we found out that the slope of the tangent line, now I'm doing it in blue here, the slope of this tangent line was 2, right? We know this equals 2 when x was 1. Well, this tangent line is a little less steep, right? So 1.4, that sounds good. So the slope here is 1.4 when x is 0.7. Okay? So we now have this formula, this 2 times x, that tells us we can find the slope of any tangent line. We can even come over here and let's see. If x is negative 1, well, if x is negative 1, we have the slope of negative 1 is going to be 2 times negative 1, which is negative 2. Okay, so does this have a slope of negative 2? I think so, because they're mirror images of the opposite side, right? All right, so there we go. We have a function that will give us the slope of any tangent line on this graph. So this is what we call the derivative. So the derivative is a very important function. This is the foundation of differential calculus. All right, so this is what we call the formal or the limit definition of the derivative. All right, when we're taking the limit of the function we just found, okay, we get the slope at the point, slope of the tangent line at the point x f of x. Okay, so this is what we call the derivative function of f of x. We write it like this, f apostrophe x, but we read it as f prime of x. Okay, and here is the definition. If f of x is differentiable, we'll see what that means here in a bit. It means we can take the derivative. Its derivative function is defined as this, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, where did that, the x plus h minus x go? Because that's what we're using up here, right? Okay, so this is just what we've been using. So we've been saying the y minus the y over the x value, x plus h, minus x. But what does this bottom simplify to? Just h, right? So this slope formula just kind of cleans up to this. So we just have h. H is the distance between the x values in that situation up here. All right, so this is what we call the derivative. We have other ways of writing this. We call it f prime of x, or we can write it as y prime, y apostrophe. That's how Isaac Newton described it and wrote it. But Leibniz, who was developing calculus at the same time, wrote it like this. He wrote this dy dx, or d dx of f of x. Okay? And so where is that coming from? Well, that comes from this. We know delta y over delta x is this average rate of change, f of b minus f of a all over b minus a. All right? And as the distance between b and a gets smaller, so at the limit, this delta becomes infinitely small, and instead of delta x, we're going to write it as dx. And instead of delta y, we're going to write it as dy. So this is average rate of change, or that AROC, AROC, can't spell here, okay, average rate of change. And this is instantaneous rate of change, there, okay. So that's the idea. Well, let's try one here. It's going to take a little bit of algebra, and we'll find shortcuts eventually, but right now let's work through it. All right, so here we got a function f of x equals x, the square root of x minus 2. Okay, so let's think about that function for a second. How does the y values change? All right, what's the graph? All right, the graph is, we're going, well, first of all, the graph of, you remember what y equals the square root of x looks like? Well, the square root of x looks like this. Okay, so if we have y equals the square root of x minus 2, so y equals the square root of x minus 2, that's going to move 2 to the right, and it says half parabola. Okay, it's always increasing, and it's only works for x is greater than or equal to 2, because if x is less than 2, well, we have a problem here. All right, so let's find the derivative using the limit definition above, or the formal definition. So the definition of the derivative, so f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. It's good to write that down, especially as you're getting used to it. So for our function, this means we have the square root of, now we're going to plug x plus h into this formula. So we're going to replace x with x plus h. And so we have x plus h minus 2. Okay, that is f of x plus h. Now let's go minus f of x. What is f of x? It's just the square root of x minus 2. And all of that over h. All right. So let's clean it up. Well, how do we find this limit? Can we just plug in 0? Let's give it a try. If you plug in 0, this becomes x minus 2, or the square root of x minus 2, and minus the square root of x minus 2. The top is just 0. So if you plug in 0, we get 0 on top. If you plug in 0, we get 0 on bottom. That's a problem. So we've worked on limits. So what we need to do is we need to multiply this by something special. Do you remember what it is? It's the conjugate. So we need to multiply this by x plus h minus 2 plus the square root of x minus 2. Okay? It's kind of ugly. Got to do the top and the bottom by the same thing, right? Because we're multiplying by 1. Okay? And let's see, what happens on the top? Well, this is a plus b times a minus b, right? Or actually, a minus b times a plus b. And we know that a minus b times a plus b becomes a squared minus b squared. It's the difference of two squares. So we have the first thing squared. When you have the first thing squared, it's x plus h minus 2. Minus b squared, that's the second thing squared, and that's x minus 2. All right? And the bottom, well, don't try to do anything with it. Just copy it down. You'll see why. X plus h minus 2 plus the square root of x minus 2. Be organized with your work. Keep track of things. Keep it in order. Okay. Well, what's going to happen here? Lots of stuff is going to cancel. Okay. So we have x minus x. Now remember, this minus gets distributed. We've had experience with that over the years, so if you want to write it out, that's good. But x minus x goes away. We have negative 2 minus negative 2. What is negative 2 minus negative 2? Well, that's 0. Those go away. What's left? All that's left is h on top. So we have h over all of this. Let's go ahead and write that out. So this equals limit as h goes to 0 of h over h times the big old ugly square root stuff, x plus h minus 2 plus the square root of x minus 2. Well, the h's here are going to cancel, right? Now leaving a 1 behind because it's h times 1. And so now we have the limit of 1 over this. Okay, well that's something we can figure out now. Okay, h's are gone. We have 1 over this big old parentheses. So if we take 0 and we plug 0 in, we're going to get this. We're going to get 1 over, h goes to 0, so this is square root of x minus 2 plus the square root of x minus 2. Wow. So that's something there. And when we add these two, we can simplify this. These are the same radicals. So if we have one of these plus one of these, we have two of them. So we can write this as 1 over 2 square root of x minus 2. And there it is. So we just found out that the derivative of x is 1 over 2 times the square root of x minus 2. What does that mean? Well, the derivative is the slope of the tangent line. So if we plug in 3 here, we have the derivative of x, derivative of 3. So the derivative of f at 3 is going to be 1 over, I'll plug 3 into that, so we have 2 times the square root of 3 minus 2. Okay, using our formula up there, let me write it down again here. F prime of x is 1 over 2 square root of x minus 2. Okay, so we plugged in 3, and we got 2 times that. Well, this is the square root of 1. So this is 1 over 2 times the square root of 1, which 2 times 1 is 1. I'm sorry, square root of 1 is 1. So this is just 1 over 2. So the slope at x equals 3 is a half. So if we look at our little chintzy graph here, okay, at 3, this is 2, at 3, the slope is a half. Okay, I'll buy that. Okay, now, my little fat line there, this is a tangent line. It just touches at that point right there. Okay, so yeah, all right, so that has a slope of 1/2. Okay, what about when x is 10? Well, we've got the derivative of f at 10 is 1 over 2 times the square root of 10 minus, what is it, minus 2? Okay. You know what, 11 would have been nicer, huh? Because that's square roots. Okay, that's okay. All right. So this is, you know what, let's go ahead and change it to 11. All right, let's avoid the decimals for the moment, and we'll get the right idea. All right, let's change that to an 11. All right. Okay. That's more interesting because it comes out to be a whole number. All right. So that's going to be 11. So this is 2 times the square root of 11 minus 2 is 9. And so that is 2 times 3 on the bottom. And so that is 1/6. So the slope at 11 out here, way out here, the slope would be, if we continued out here, okay, somewhere out here at 11. So we'd have a slope, it'd just have a little bit of slant to it, okay, and that slope would be 1/6. Okay. And so on and so forth. So the slope is declining, all right? So a couple more real quickly. The derivative at 27 is 1 over 2 times the square root of 27 minus 2. Okay, that's 1 over 2 times the square root of 25, which is 1/10. Notice the slope is getting smaller, right? Okay, so it is increasing, but the slope is gradually getting smaller. So the slope's always positive. It's always going up to the right, okay? But it's going up slower and slower. So this is the instantaneous rate of change. When x is 27, we're just going up, and we're going up at a slower pace, we could say. All right, how about one last one? So f prime of 2 is 1 over 2 times the square root of 2 minus 2. Well, that's the square root of 0, which is, does not exist. Because we have 0 on the bottom, so 0 times 2 is 0. Can't divide by 0. That doesn't exist. It's undefined, all right? Okay, so undefined might be even a better way to say that, okay? So it's undefined. That means we cannot take the derivative. Here, what's the derivative? What is the slope there? Well, we can't actually find out, all right? So we say this is not differentiable at x equals 2, okay? So we say this. Describe which values f of x is continuous. Well, it's continuous for all numbers from 2 to infinity. All right? So it's continuous on that interval. However, for what intervals is f of x differentiable? Okay. Well, you know what? Actually, we should say this. Let's clean this up. Make this a little bit, okay? So it's continuous on this closed interval because it's defined. So that should be closed on 2 there, all right? And so it's differentiable. We say we can take the derivative, differentiable for x is greater than 2. Or we could say from 2 to infinity. But at the point 2, we cannot take the derivative as we just saw. All right? And anything less than 2, we can't take the derivative because the point doesn't even exist. Okay? All right, one last thing. How about the equation of the tangent line? Well, we know the derivative of f at 27. We already found that out up above. That was 1/10. All right, what is f of 27? What is the y value at 27? Well, the equation was the square root of x minus 2, so 27 minus 2. That's the square root of 25, which is 5. And so that means we got the point. It goes to the point 27, 5. That's on the graph. So we have a point and we have a slope. So remember, this is the slope. Okay? So we got the slope on the point, so we can use point-slope formula. Remember what that is? Y minus y1 equals m times x minus x1. Okay? So our equation is y minus 5 equals 1/10 times x minus 27. Now, if we wanted to put that into slope-intercept form, we could. We could distribute this out, and we can write it as y minus 5 equals 1/10 x minus 27/10. And we could add 5 to both sides. And we could get y equals 1/10 x, and that's 10/10. So this would be, I believe, 17/10. Okay, but we usually don't care to do that. We don't need to. You should be able to, but we don't need to. This is fine. All right, well, there you have it. So that's how we find the derivative using the formal definition. Takes a little bit of algebra, sometimes a lot of algebra. But if we write that, we can find we're finding the slope as the distance between the two x values becomes 0. So as h becomes 0. Now we will be finding shortcuts soon, but for now, this limit definition is our only tool to find the derivative. So keep working on that algebra and be patient and don't be afraid to take up a lot of room and you'll get it. Great job. Thanks a lot.